Hello everyone, thank you for joining today's MOLDEX 3D live webinar. Today we'll be talking about case studies focusing on shrinkage, weld line, and stretch mark. We're having John Lin, he's our account manager at the MOLDEX 3D EMEA, to present today's topic. So before we start, there are a few things that I would like to remind you. First, please keep your microphone muted. Second, if you have any questions, you can use the chat box to send them to the host. We will select a few and answer them at the end of the session. Lastly, if you'd like to get a recording, please don't forget to join our survey that will be sent after the webinar. Now let's welcome John to start today's presentation.
Hello everyone, I'm John Lin from MOLDEX 3D, and today I would like to share some real case from our customer and how they solve the defect from the reality by using the software. Okay, today we have three cases. One is the stretch mark issues, and the second one is uneven shrinkage, and the last one is wear line issues. Okay, the first one, the stretch mark. And in this one, you can see that they have a surface defect. And at the very beginning, they didn't know what this kind of defect is. Yeah, it's just surface defect. They didn't know it's a flow mark or stress mark, or maybe it's caused by the material. So here is the basic information is the material is ABS, and the average thickness of this part is 2 millimeters, and you have a very simple cooling channels on the top and bottom of the cavities. So they think maybe this caused by the flow. So they check the mill front time, but as we can see here, it looked quite smooth. So it doesn't observe any hesitation issues, or we can just use this ISO contour display methods. We can check the line in between. So each the distance between each line means the same time increments. So if any lines getting closer, it means that there's a hesitation issues. But you can see this the distance in between each line is quite equal, so it doesn't have a strong hesitation issue in this case. So it's not really a flow mark problems. And then they try to check the temperature in this cavity, and they find out that there's a hot spot nearby the gate regions, and the temperature difference is around 9 degrees from the center of the part to the outer of the part. And then they check the residual stress of this one. They can see that there's a high residual stress on the bottom and the tops of the cavities, and it matched to the problem in the reality. And they think this one is the stretch mark, and it's caused by the poor temperature distribution inside the cavities. Okay, so they come with a solution. First, they find out it's not the flow mark caused by the hesitations, and this issue is caused by the residual stress and related to the temperature distributions. So using the conformal cooling should fix these ones. And then they come to this new conformal cooling design to remove to make the temperature more uniform inside the cavity. And you can see that it's roughly 3 degrees difference. And if we look inside the cavities, you can see that the temperature is quite uniform compared to the original ones. And then they go to check the stretch mark. You can see that is so much lower than the original ones. So they use this design for the toolings, and yeah, the stretch mark just be removed. Okay, this is the first case. And the second one is the uneven shrinkage issues. So this part is sort of covers, and at the very beginning, they find out that the dimension on the top and bottom have a difference and it's not acceptable to the criteria. Right now is 0.15 millimeters. And here is a basic information of this part. The material is a PC, and the thickness is quite small. It's around 0.85 millimeter. And here you can see the basic process conditions. Okay, and they try to check the mill front first, and they find out that maybe I can. You can find out that here we have a fast flow. Even that the runner look quite symmetry on the top of the systems. So in this part, it looks quite symmetry, but this kind of runner system will have unsymmetric flow due to the shear heating issues. So if we actually look the mill front in the other side views, so you can see that here it's faster on this part. And then if they check the temperature result, so this is what I meant, the shear heatings. So if we check these ones, and it's here, so you can see that the higher temperature go to this way, and on the other side, this side, the material have a lower temperatures, and then it keep going to these junctions here. So it will be pictured this way. So you can see that one side of the runner have a 320, 330 degree, and the other side is 315, 314. So this one will have a higher temperature than this one. So this one will go faster. And if we check the mill front temperatures in this part, you can see that the temperature is very interesting. It's one side is hotter than the other side, and this one is because it's caused by the shear heating issues. So now they find out that the problem is caused by the shear heatings, so they use this mill flipper features or geometries, try to remove the uneven temperatures issues. And they have two different design. One, they add this mill flipper in the here, and the other one, they add mill flipper every time when the mill front gonna split to two directions. So here you're gonna split to two directions. They add the mill flippers, and again, this one gonna split to the other twos, and they add mill flippers. And they find out that in the real mold trial or in the simulations, they can see that one side still faster than the other side in the solution one. Only solution 2 can have a balanced mill front in both simulation and realities. Okay, so they go for these ones. Okay, so they can see that yeah, so each one is quite balanced. And if we check the temperature results, so the most important thing is these junctions. We need to make sure that the temperature in this side equal to this side. So if you check, is here. So the temperature is 180, 380, 320. And on the other side is 317, 322. So it's not exactly the same, but the difference is quite less, maybe 1 to 2 degrees difference. compared to what we have before is like 10 or 20 degrees difference. And then they can check the mill front temperatures. You can see that is more uniform in this solution too. And the uniform temperature distribution will provide more uniform viscosity, and the pressure can transfer uniformly inside the cavities. So at the end, this one have a very good dimension, very similar dimension on the top and bottom of the cavity. The difference is around 0.01 millimeters. So in this case, they have an uneven shrinkage issue, and they find out that the uneven shrinkage is caused by the uneven flow patterns. They try to make the flow balance at the first, and if the flow is balanced, the packing effect should be similar inside the cavities, and it will lead to a better shrinkage or more uniform shrinkage result inside the pot. Okay, the last one is the weld line. And in this case, the weld line is not really just a defect issues. This weld line actually caused the component unfunctional. So this one is some electronic components. So it's a very, very small design, and the thickness is very small. It's 0.6 millimeters, and the material is a PA9T. And in some regions, okay, see that in some regions like here or the others, the thickness is super small, like 0.09 or 0.06. And before we run a simulation, we can imagine that when the material passes these features, the material will cool down very fast, and it might have very bad welding line qualities when the mill front passes these features, because there's a hole in the middle in here, so it must create a weld line around these pins. It depends with the flow directions, but yeah, we can imagine for sure there was a weld lines. Okay, so in this case, the real problem is not really the weld line. The problem is the weld line lead to some kind of like crack or some gap on one side of the pot, and they have to hire a fire operator to do some checking process. They just drop some red ink on this side and wait for a while. If the ink flow to the other side, then this one failed, because this kind of behavior will make this functional area non-functional. So to them, there's an extra cost to hire another operator to proceed this kind of checking process. And even that, they find out that only roughly 60% of the part passed the testings, so they need to throw the other 40% of the part away. So it's a lot of wasting. And the other one is a long cooling time, but long cooling time is not really a must. It's a must fix issues. It's just a plus. Maybe they can make this one shorter. That would be a plus. But the real problem is the this crack or weld lines and caused the part unfunctional. Okay, so the part is the quality is not stable. So you can see that half or 60% passed the testing, and why not is not 0% or 90% failed. So they checked the mill front time, and in the original runner design is a not very good one. This one we call is a fishbone design. For sure, it will cost less, but the flow length from the inlet to the first cavity is so much different than the other ones. And so those two will fill first, and the other two will fill later for sure. And when those two fill completely, it will go into the packing phase. And the material will be for sure lower temperature to fill these four cavities. And this component is a very thin design, so it should be very sensitive to the temperature distributions. So if they want to make the quality in each cavity the same or similar, they need to change their runner design to a balanced design. Okay, you can see that. So here, this one go fast, and the outside goes later. Okay, for sure they have weld issues, and if the gates here, and you can imagine that the mill front will go these directions because there's the sink features here, so the material will go very slow in these features, and when those mill front meet here to create the weld lines, the quality of the weld line will be very, very bad because the temperature of the mill front will be very, very low when they meet each others. And it might be the problem why they have the crack, because the poor quality of the weld line. Okay, and by the way, they think the cooling time is too long for this kind of design because for the cavities, it only need 1 second or less than 1 second to cool, but they need to wait another 6 to 8 seconds for the runner system, and they expect this one can be shorter. Okay, so now the problem is quite clear. They have an imbalance runner system, create an imbalanced flow, and then the quality in each cavity is not the same. And they have a weld issues, and it will be related to the thickness design. If they can remove the sink features, make the thickness more uniform, and they might able to provide better weld-like quality, and maybe they can fix these issues, the crack issues. Okay, first they try to change the design. Originally is a fishbone design, so it goes these directions, and now they change to the S type. So the flow length to this one and this one will be similar. So they expect that the mill front will be similar, and the others like pressures, mill front temperature will be similar too. Okay, so yeah, actually when they check the mill front results is similar. So they also check the temperature distribution in each cavities. You can see that yeah, it's quite the same in each cavities. And also in the temperature, this one's temperature result is also very similar in each cavities. So if the pressure, mill front time, temperature is similar, they can expect the quality in each cavity is similar. And then they also, when they do this kind of change, they also change the cross section of this runner and to a smaller one. So it require a shorter cooling time, and it reduced from 8 seconds to 5 seconds. And for this kind of design, the whole process is 13 seconds. So if they reduce 3 seconds, it means they can produce like 20, maybe 25% more product in the same period of time. Okay, and then they try to actually test this kind of S-type runners, and you can see, yeah, it's quite balanced in each gate. And this one is the original ones. So those two will always be faster. And because they change the cross section of the runners, so the total weight of the runner will be less, so they can save some material. Okay, it's another plus. It's a good thing. Okay, then the next one, they remove these features. In the original design, they have this rectangular shape and thin features here. Yeah, in each pin, around each pin, they have this kind of design. So they remove the design and change the pin to a round shape. And also, yeah, this one is not really the solution, but yeah, they change this too. The main solution will be fixed by changing the features near the pins. So when the thickness become bigger, the millfront temperature will be higher when the two millfront meet each others. So if we check these ones, okay, so yeah, for sure we have a pin here, and yeah, we can expect the weld line somewhere here. Yeah, but once we remove the features and we have a more uniform thickness, it will not have a hesitation issue near the pins, and the quality of a weld line can be improved, and maybe they can fix their crack issues. Okay, and they actually try it, and in original design they have a crack here, and then with a new designs it's good. And they also do the test of the ink. They drop the inks in here, but yeah, all of them is fine. So after they improve the runner and the cavities, and when they check it, almost 99 cavity passed the testings. And the cycle time reduced like roughly 30%, and the runner weight reduced like 11%. Okay, so that's how they fix the problem. First, they find the quality is unstable in each cavities, so they find out that the problem is caused by the unbalanced flow or the unbalanced runner design. They improve it to make it balance, and then after each cavity have a similar quality, they can try to fix the weld line issues. And by fixing the weld line issues, they change the thickness near the pin, because in the original design the thickness is too small. It's less than 0.1 millimeters, and the material will have a very low millfront temperature when it happened when the weld line happens. And once they remove the thin features, you have a better weld line qualities. It mix in the higher temperature, the quality is better. Then they heal the crack issues. Okay, so that's the case I want to share today. And if you have any questions, please feel free to ask.
So thank you, John, for the short presentation and case studies. So before we jump to Q&A, there's a quick promo to our upcoming webinar. On December 14th, we'll have a topic focused on gate design and runner design using our latest MOLDEX 3D software 2022. So if you need to know more about this, you can sign up. The link will be pasted in the chat box. So now back to Q&A.
Okay, we have a few questions. The first one, how to minimize weld line death? To weld line issues, usually it's related to the flow patterns, and the flow pattern will be related to your part design, your thickness distributions, or your gate locations. So if you want to change the quality of weld lines, like this case, it change the thickness of the part to change the weld lines. And the other thing we can try is change the gate locations. So it might change the mill front patterns, change the meeting angles, and it will change the weld line length. Okay. Okay. The next one will be, what software should you use to get best results? Okay, that's a big question. So basically, it's very difficult to define best result, because a best result, it require the correct input, and not just our solver types. And here comes some selections. Should we select enhanced P or standard? I will always go to the enhanced P. The standard is our old solver kernel, so normally I only use the enhanced P. And for the advanced options, accurate selected. I guess it's accuracy. I will stay with D4. If your part is a very small part or a very unique part, I will go with 1. The solver accuracy with a 1. If we need the ventings, the venting, sure, if you have real venting conditions, then yes, we can select the venting. But in most of the case, our user doesn't know where is their venting. Then at that situations, then the venting is not necessary, because we don't know what is the real venting systems. And the wall sleep BC, usually I will skip this one. I don't use the wall sleep, because it's very difficult to define the wall sleep boundary condition too. And the extensional viscosity, I don't use that for general case. I only use that for some like case studies. For general case, I want to have a simulation result. I will not use this extension viscosity. Okay, here comes the next question. In those cases where the representation of the rounder is quite important, do you use CAD or line to model them? Actually, those cases are run by our customer, but when I check the PowerPoint from them, it looks like it's a line runners. So if it's possible, I also recommend to use the line runners in your simulations. Okay, here's the next one. Why not go for hot runner system instead of a three-plate mold? For this one, actually, the mold is chosen by the customers, and I think they have some budget issues, so they choose the three-plate mode. The hot runner usually costs more. Here's the next one, how to reduce the stress mark in molding process without changing the product design. But in our case study 2, it doesn't change the product design. It only changed the cooling channel. Sorry, the case study 1. You only change the cooling channel. You only change the mold design to provide a uniform temperature distribution in the cavities and reduce the residual stress. And furthermore, it fixed the stress mark in case 1. Meal flipper is patented. I maybe I should not use the meal flipper. Maybe it's a special names, but the idea is to change the flow temperature distributions. And we also have another question: how the meal flipper works. Maybe we should not just use the meal flipper, but maybe I can explain in here's how we can use the runner system to change the temperature distributions. Yeah, I don't really have a case here, but okay, maybe I will try it. Hmm. Not easy to explain in a PowerPoint, but I will try. Okay, so okay, this one is let's see, is a top view of the runners, and we have inlet here. So the temperature is higher because of the shear heatings, and inside will be coolers, and it goes years. The temperature will be higher on this side, so it's hot, and this side is not. It's a cold. Okay, cool. Okay, so when we go with meal flippers, for meal flipper, or when we change the direction of the melt, I need to draw a picture in 3Ds. So, okay, I have a runners, and you go up, and you go down, and then okay. So I hope this picture we can explain how it works. So okay, I have drop here. Okay. So the shear heatings, we have a higher temperatures. This close to the walls, and in the middle is the lowers. So when you come to here and go up and go down, so we have a higher temperatures on this side and this side. When you go to the two directions, so we can see here we still have a higher temperature. In the middles, we have a lower temperatures. But if we check the other sides, you can see the same behaviors because we change the direction of the mills. So because this one is go from the top to down, and it will split to two directions. So we kind of a similar temperature distribution in two sides. If we don't use this kind of a design, try to make the melt go up and down, then it will simply have two different temperature distributions. So it doesn't have to be this shape. I also see something like go down and go up. So the idea will be try to add some things to make the mill front is go in the vertical directions. I also noticed in some good hard runner systems, they will always go like, so they have a hard runner, maybe like this one. So it doesn't simply okay. If they need to design something like this, you have an X and let's go down. Okay. So they don't simply create this one. They will always add something here. So they will add a sections. So it's not in the mill is not split in the other direction in the same labels. It's not in the same label. It's in different labels. So it adds one sections here and split the mill front. So you can see actually the mill front direction is from up and down, and then split to four directions. So this one, I noticed a lot of a hard runner system, they like to use this one. And actually this one is a similar idea to this one too. So you change the flow direction, not in the horizontal directions. You make it in the vertical directions, and it will not 100% fix the shear heating issues, but it can reduce the shear heating, the flow imbalance caused by the shear heating. It can reduce it. Okay. Okay, next one for the shear, for the stress mark, you see the warpage result or packing result or injection result. I would recommend to check both to make sure there's because the residual stress can caused by the thermal and caused by the flow. We need to check both and to make sure both of them is fine. Okay, the next one, a stretch mark happens because of the sharp edge on the part or any other reasons. I would say in some case, yes, the sharp edge on the part will cause the stretch mark. But in this case, the case I shared in case one, is more caused by the temperatures. And yes, the sudden change of the thickness will cause the temperature difference. And yeah, so it's related to the sharp angle edge, but most normally is related to the temperature distribution and cause the high residual stress on the part.
Okay, I think we answered almost all the questions, but if you have further questions, you can still use the survey that will be sent shortly after the webinar. So thank you very much again. That will be wrapping up of today's event. We hope to see you soon next time.